hello world. Here we go. Share screen. Okay, thank you for pointing out my screen wasn't shared. All right, so here's the problem. It's number 13 in homework 2.1. I'm going to copy that into my notebook to play with. And might as well get the question. And what do we got? So a survey was given asking whether they watch movies from Netflix, Redbox, or a video store. Are there still video stores out there? Use the results to determine how many people use Redbox. Hint, draw a Venn diagram. I miss walking around video stores and looking at the boxes and picking stuff. Anyway, okay, so we have Netflix, Redbox, video store. Are there other options for video? The answer is yeah. So I should consider that I'm going to draw a universe around this where there could be people that don't use either. So we draw our universe. Our universe would be, I guess, people that watch movies. And then, oh, where's my magic whiteboard? There it is. Okay. Oh, by the way, I guess I should show this. I'm going to unshare for a second. Stop. Okay, question number 12 also. Thanks, Mason. Can you see me? So for those of you who are going to be teachers in the future, there's all kinds of technology for writing. So I have this stylus tablet here that I can't see the screen on here. I just have to write on it, and then what I write on here appears on the screen. So I watch the screen while I write on this tablet. I like it because it's relatively inexpensive. They're under $100 and it's a reasonable size. Otherwise, you need some kind of, there are screens out there, big and small, that you can write directly on, and they digitally are projected somewhere. Like a lot of elementary school classrooms have smart boards in them that are big. Otherwise, people write on iPads and things like that. So you're ultimately going to use some kind of digital technology when you're presenting to kids in person or remotely. By the time you guys start teaching, I'm pretty sure we're going to be back in the classroom. It might be different than it used to be, but we'll be around real people again. But I'm thinking it's not going to be for like a year. Don't let that depress you. We'll get through this. All right, back to the whiteboard thing. And the one I have is called it's from a company called Wacom. I do not endorse Wacom in any way. There's tons of other ones out there. Somebody just bought this for me. All right, share. It's not a commercial, by the way, not a commercial. Just an interesting use of technology. All right, so I have 3 subsets here. I have one for, let's call that N for Netflix. Capital N. I'm going to have another one here. Let's call that an R for Redbox. I do see Redboxes around. And then we'll say this set down here is V for video store. And then we have to then process this language up here to try and figure out what's going on. I mentioned before that it's almost always easier to work from the inside out of these Venn diagrams that have multiple sets. So the 8 that use all 3 is, I think, where I'm going to start. So I'm going to put 8 in the middle here. So those 8 people use Netflix, they use Redbox, and they use video. They use all 3. So I got that. So on my notebook paper, I would have written down all of this information on paper so I can kind of check things off as I go. Let's see, what else could I use? 44 use only Netflix and Redbox. So if it says they use only Netflix and Redbox, I think that's pretty clear they don't use a video store. They only use those 2. So Netflix, Redbox only should be this region up here, 44. I can make a new statement based on this 44 and 8. I could say that 44, no, I can't, I lied. What's 44 plus 8? That would be 52. 52 use Netflix and Redbox, capital R Redbox. Notice the difference. If I drop the word only, it doesn't say that they don't use a video store, okay? So I don't know. And so that would be that 52 is this whole region right here. So the word only is important there. That came up in the last class when we were talking about a problem I think might have been misstated, but we got through it. So I got that. 23 use only a video store. Okay, if they use only a video store, they don't use Netflix, they don't use Redbox, so I think those 23 would go over here. All right, this problem isn't as hard as I thought it was going to be. 55 use only Netflix. Okay. What else do I got? Check. 44 use only Redbox. 14 use only a video store and Redbox. Video store, Redbox, 14 should be right here then. So let's say I got that. 28 use only video store Netflix. So video, Netflix, 28 should be right there. Check. 17 use none of these, so those 17 would be out here. Check. So for people who used Redbox, that's everybody that registered in the Redbox area, which came from other subcategories. So that would be the 44 plus this other 44 plus the 8 plus the 14. So what do we get? 44, 44, 14, and 8. Add those suckers up. 4 and 4 is 8, and 4 is 12. 2, that's 10, carry the 2. That would be 10, 1, and 1. 110, use Redbox. All right, so using a Venn diagram to try and sort out information to get other information from it. So there's all kinds of questions we could ask here. So let's see, what would be another question?
Did you have one about the teachers? There was one with teachers that had me kind of stumped. It was the one where like so many teachers work at one school and the other teachers work at, that one was kind of hard for me.
Yeah. Well, let's take a look at that one too. So this was number 13. Let me make a note of that. Number 13, homework. Oops. Homework 2-1. All right, and then Mason mentioned 12, and I think the one you mentioned was 14. So I'm going to back up to Mason's. Okay, let's take a look at this one. And the numbers will be different each time we load these things, so yours won't be exactly the same as mine, but it should be similar. Oops, button again. Someday I'll get this down. All right, I think I just need that part. Okay, what do we got here? We have the number that are in A complement and B complement. Okay, so the set we want to reference is pen. Come on, pen. A complement. Wow, what is wrong with my pen today? Maybe I should have rebooted my computer before class. A complement. So that's everything outside of A. And we want to intersect that with B complement, which would be outside of B. So where does outside of B and outside of A meet each other? So maybe I'll do that with some shading in, let's try blue today. So outside of A, let's go horizontal shading for that, and then we'll do vertical shading for outside of B. So outside of A would be like this. So come up with some scheme for denoting what the referenced regions are. All right, so this is everything outside of A. Then I'll go the other way for outside of B. So outside of B would be all of this. And some people just get this. They just look at it and they see it. I'm not always one of those people. Usually I have to work pretty hard at it. So just shade in some recognizable way what it looks like to be outside of the B circle. So that would be all of this. And I want to know where these two shadings intersect. So that means there has to be both vertical and horizontal shading. So let's see, out here, so I'm just gonna kind of scribble to make it more obvious. Out here for sure, over here, over there, over here. Yeah, it looks like everything outside of the figure 8 those circles make has the two combined intersect. All right, so what numbers are out in that region? Now that I've scribbled on it so much, it's going to be harder to see. There's the 9, and then it looks like there's a 5 down here. Okay, so it's got to be outside of A and outside of B, is what that says. So 9 and 5. It looks like for mine, there's 14 outside of set A and B. And then sometimes I have to redraw the picture to you know, reassure myself because I made such a mess there. So I'm just going to do that again, double check. A, B, and C down here. And let's go shade again. So yeah, so this part of set C is outside of A and B. And then anything out here is outside of A and B. Yeah, so that would have been just the 9 here and the 5 there. Okay. So usually I have to kind of break down, try and figure out what each piece is and then how to connect them. Does that help? So just for fun, let me get some points. Okay, and if I redo it, it's the same question, it's the same question. Oh, cool, good. All right, so next one mentioned was, oh, there's a chat. How do I lose my chat? Okay, thank you, that helps, got it. All right, and I want my participants list. All right, and still missing a couple. All right, so does this is the one mentioning teachers, so I think this is what you meant. I think it was Amanda that asked. Let's screenshot it. Oh no, I feel a sneeze coming on. Don't do it. All right. Suppose Albers Elementary School has 63 teachers, Bothell has 37 teachers. If 4 teachers are at both Albers and Bothell, compute the total number of teachers employed at Albers and Bothell combined. Oh, cool. This is a fun one. So I'm going to draw my universe, although I don't think it references anything outside of either school. So draw my best rectangle out here. And then in this case, I just need 2 subsets. So one subset will be for A for Albers, and the other subset is set B for Bothell. Albers Elementary School has 63 teachers. Now those 63 are somewhere in the circle here. Some are in the intersection and some are not. Bothell has 37. Some are in the intersection and some are not, but then they say, hey, 4 teach at both. So the number of teachers that are at Albers and Bothell is 4, so I can put 4 right there. So if Albers has 63 total, 63 minus 4 would give me 59 on a good day. 59 plus 4 is 63. So there's the total 63 that are at Albers. And then Bothell has 37 teachers, but 4 of them are already accounted for. So that leaves 33 that were unaccounted for. 33 plus 4 gives me the 37 that teach at Bothell. Now, the final question says, how many are at both combined? And mathematically speaking, that would be a union. So if we took all the teachers at Albers and made a union with all the teachers at Bothell, like we lined everybody up, we can't count people twice. How many are there going to be? Well, there would be 59 plus 4 plus 33 altogether. So what's that? 59 and 4 is 63. 96 in my instance, and it could be we have different numbers each time. So it looks like there are 93 at both schools combined. All right, Avali's here. Welcome. I'm glad you could make it today. Sorry about the confusion on the last class. All right, so this is number 14 from homework 2-1. All right, were there any other homework questions? We took a look at 12, 13, and 14. Otherwise, I think we're ready to jump into logic. Okay, logic, here we come. So we've already actually done a little bit of work in logic, and I'll explain how and then what we're going to do next. So new page, section 2.2 on our book. Hopefully you've at least started reading it. The reading assignments due today is on an introduction to deductive reasoning. What we have been doing so far, among other things, is we've already done some inductive reasoning. And I'll try to explain the difference. So inductive reasoning is taking specific examples and coming up with general conclusions. And this is a pretty broad field. We've only done a little bit of inductive reasoning. And so, for example, one thing we've done is when we looked at patterns like 1, 3, 5, 7, we decided, oh yeah, we see a pattern here that we just keep adding to starting at 1. And that leads to a formula if we consider that this is the first term, that's the second, that's the third, that's the fourth. So any n down the road, where n could be 4 or 100 or 1,000,000, the answer should be 2 times the position n and then minus 1. So I took a few specific examples here and I formed a general conclusion here. So that's an example of inductive reasoning that we've done. Deductive reasoning, on the other hand, is kind of the reverse in a sense. Is taking general conclusions and then with those forming specific facts, say. So an example of deductive reasoning, and we'll do a bunch of examples like this today, would be to take a statement like all people from Rhode Island spell poorly. Barry Parker is from Rhode Island, abbreviated RI. So then from those two statements, I can draw a conclusion. Gary is a poor speller. Okay, so I took some conclusion, some facts. All people from Rhode Island are poor spellers, they spell poorly. Gary is from Rhode Island, so Gary is a poor speller. So if the first two statements are called premise statements, and from the premise we try to draw a conclusion. Now, just because somebody tries to draw a conclusion from a premise doesn't mean it's necessarily true. The premises have to be formed properly. And so we're going to explore what it means for premises to be formed properly, to draw a proper conclusion from them. And then there's a bunch of homework problems on that. All right, so with deductive reasoning, we deal with a lot of statements of fact. And so let's talk about statements. So we're talking about logic, and logic is like the math of language. So in logic, we have the idea of a statement. And really a statement is really any sentence. A sentence could be a very simple sentence like Gary is from Rhode Island. Or it could be a much more complicated sentence or statement. So for example, if the sum of the digits of a number are a multiple of 3, and the number is even, then the number is divisible by 6. So that's a statement, it's a sentence. It's much more complicated than the sentence, Gary is from Rhode Island. Gary is from Rhode Island is about as simple as you can get with a sentence, right? We have a verb, we have a subject, we have an object. And then in this other one, we basically have 3 sentences strung together with some connections, if, then, and. So you could consider, I could break this up into 3 different sentences based on the if, the and the then. So a statement's a pretty general thing. We can have an idea called a simple statement. Which could just be a subject, a verb, and an object. And then we can, build those up with other modifiers and conjunctions. And so we're going to kind of play around with that idea, bouncing back and forth between these very simple statements that we can connect in more complicated ways to talk about ideas in our world that are just plain complicated. And most of our world is just complicated. And it turns out there's all kinds of rules that apply to how these connections work together. And one can demonstrate that things are true or false based on these other kinds of rules. So let's see. Other things I wanted to mention, yes. So we're going to stick on simple statements for a little bit and then move up to more complicated ones. Things we can do with statements. So statements, say modifications. In the simple sense, we could take the opposite of a statement. So the opposite of Gary is from Rhode Island would be Gary is not from Rhode Island. Another statement we started with before, let me go back for a sec. Let's see, all people from Rhode Island spell poorly. So the opposite of all is actually some. And then the opposite of spelling poorly is, I would say, not spelling poorly. So some people from Rhode Island do not spell poorly. Sometimes we want to replace not something with a different word, and we have to be careful with that. So I want to give a couple of examples of why. So some might say the opposite of spelling poorly is spelling well. Is there something between poor and well? One might argue that mediocre is in between poor and well, and therefore if we jump from poor to well and say there's nothing else, we could be wrong. So I didn't change this to spell well, I just put a not in front of spell poorly, because maybe it's more complicated than one or the other. So it could be, as far as spellers go, there are categories like poor, mediocre, which is like average. I don't think I spelled that right. Oh, maybe I did. I'm gonna have to look that up. And then well, okay, or I could say average, how to spell that. So let's look at a similar example. Let's see, how about, very simple sentence, a number is even. So what I would like you to do is I would like you to negate this statement. State its opposite. Negate this statement. So write down what you think the opposite of a number is even would be. So first just write it down on the piece of paper. And then I will take some suggestions on it. Either you could speak them in just a moment, but give everyone a chance to write. All right, and it's a very short sentence. I'm hoping people had enough time to write something down. If somebody would like to either speak or write in the chat what they think the negation of a number is even is. And I think there's at least 2 correct answers here. Some numbers may not be even. Okay, thank you. Anyone else? A number can be odd is another, okay. A number is not even or a number is odd. Okay, got a bunch. Cool, all right. So I'm gonna write down a couple versions I have and then we'll talk about some of the other ones we got. So when we negate a statement, we wanna negate it as simply as possible. And the simplest way to negate this statement is to change is to is not. So a number is not even. That would be the simplest negation of this right here. I just reference a number. I don't say some numbers. I don't say all numbers. I don't say no numbers. And so there's really not much I can change about a number. I'll talk about how to negate some, none, and all in a minute. So I would leave a number alone. I would change is to is not. And then some might look at this statement and might say, oh, do I know a word that means not even? And a bunch of you use the word odd. Okay, so then I have to think, is not even always odd? Now, it turns out that depends on the context. So if the context here was whole numbers, so let's throw a context like a universe in here, like with when we're doing sets. Then later we'll talk about this, but it turns out a whole number is either even or it's odd. There is no other choice. So if the context was whole numbers, then I could say, yeah, another way to negate this would be a number is odd, if I assume odd means the same thing as not even. Now, there are numbers that aren't whole, like fractions and decimals. Let's see what just happened. I got a ding dong, so somebody came or left. I'm not sure what happened. Okay. So what if the context was not whole numbers? So if it is, then yeah, that would be a valid negation of this. But if the context was any number, so change the context, let's do that in green down here. Context definitely matters. All types of numbers. So that could be like pi is a number, and 2.123 is a number, and 7/16 is a number, and only whole numbers are designated as even or odd. So pi is not even, but it's also not odd. 2.123 is not even, but it's also not odd, and 7/16 is not even, and it's also not odd. So if the context was all numbers, then this would not be a valid negation. So sometimes negating statements is pretty straightforward. Sometimes it's not. When we try to do a little bit more than the basic, then it gets more complicated. So we've only been talking about whole numbers so far, so I would accept a number is odd today. But next quarter, when we're talking about fractions and decimals, that wouldn't be a proper negation. So not even. So let's do another one of those. And so think about whether what you, oh, Amy got kicked off and is back. Yeah, internet in the world of COVID. Eek. So let's try, let's go, just gonna do a number again. Numbers are kind of easier ones. A number is positive, period. And so what we want to do is we want to negate this statement. So do me a favor and on the piece of paper, write the simplest negation you can write about this. And then we'll talk about whether it could be rewritten some other way using other words we know. Anybody want to take a shot at the simplest negation of this statement, either in chat or a number is not positive? I got a few people that threw that in there. Yeah, that's the simplest negation here. A number is not positive, period. That's awesome. That is the simplest negation, and that's kind of what we should stick to. Now, then I get thinking though, right? We always get thinking about stuff. We get these ideas. And my idea is, well, you know, when I think about positives, I also think about negatives. So could I say, question mark, number is negative? So that's going to lead me to a new statement, which I'm going to test the validity of. All numbers are either positive or negative. So if this black statement I wrote is true, then the opposite of a positive would be a negative, so not positive is negative, so this blue statement should be an adequate negation. Question, is this statement true, that all numbers are neither positive nor negative or negative? No, says Jimmy. What's up, Jimmy? Help me out. 0, yeah, 0 is neither positive nor negative. So sometimes we have these ideas in our heads like, oh yeah, the opposite of this is that, but there can be cases that don't match that. Like it's not either you're a poor speller or a well speller, you could be just an average speller. So there's sometimes stuff in between. 0 is in the middle, right? So this statement is not true. It's false. This statement right here in blue is also false, okay? So if this green statement was true, so let's just, I have a number, it's in my head, that number's positive, right? So let's just assume true on this first one. If that was true, then the number is not positive would be a true negation. A number is negative would not, right? So this is false right here. That would not be true. And it turns out this is false right here because there are some numbers that, oops, missed a letter, that are not positive and not negative. And some people sometimes take exception with my statement right here. Some numbers, because some numbers are, this did not make sense, because some numbers, I didn't need the word that there, are not positive and not negative. All right, so besides that shouldn't have been there. Some people would still take exception of my statement here because I wrote some numbers and Jimmy only offered up one number, 0. So this is another important point in math. What does the word sum mean? In math, it means one or more. Okay, so 1 can be sum in math. So a statement that says something about all can be proven false if you find one example. So with that in mind, the negation of all is sum, because all you need is sum to prove that all is false, is kind of the way that works. It's a true-false dichotomy. Let's see, what's another one? And then another important but little known fact, the negation of sum is none. And just quotes for emphasis there. Because to undo sum, I just have to show that, nah, there's nothing there. So those are some little weird spots about negation, that not something, we just might need to leave it as not positive, because the opposite is more complicated than just one or two cases. So it turns out not positive is positive or negative, okay? So with that previous example, not positive, oops. This way, numbers can be positive, negative, or 0. And there are a lot of situations where there's more than 3 categories for a situation. And so my point is, when we're negating a thing, a group, an object, the simplest thing to do is just throw a not in front of it, and that gives us a negation. All right, so those are some basic ideas about logic. The next biggest part of logic I want to get to is the idea of an implication. And then we'll play around with Venn diagrams in logic. Implication is also known as an if-then statement. And what an implication is it's written in a few different ways. If we have some statement, then we have some other statement. Sometimes an abbreviation for this is if P is some statement, then Q would be some other statement. So sometimes we let a letter represent a whole simple sentence. Another way to write this would be a P with the word implies next to it, and then Q comes next. Often it's written as P with an arrow and then Q on the other side. Algebra of Logic is kind of stable, but kind of not. In some books, it might be a double arrow. It just kind of depends. So an example, or a pretty simple one for math, would be if a number is even, so a number is even is just a very simple statement, as simple as I can get, then the number is divisible by 2. Squeeze that in at the end there. So if a number is even, then the number is divisible by 2. So I have a simple statement, a number is even, and then and then another simple statement over there. A number is divisible by 2. Alternate ways of writing that would be a number, oops, is even implies the number is divisible by 2. Sometimes you'll see people sort of kind of flip it, but not really. So I could also write a number is divisible by 2 if the number is even. And this third one is often confusing because I changed the order. However, notice what the if is still with. The if is still with being even. I didn't change that. So these 3 statements here are equivalent ways of the same idea. Equivalent, they mean the same thing. So I'm going to give you another statement, and then I want you to try and rewrite it in these 3 ways here. So let's see. Hopefully you wrote this down. If not, I'm going to sneak the statement in up here. So you try it. So here's my statement. If it is raining, then I am wet. So what I'd like you to do is take this statement right here and write two equivalent statements similar to the red and blue one. So I started with the green one. That's like this first one. See if you can write it so it means the same thing and in two different ways. And then I'm going to show you some ways that are not appropriate to rewrite it, but are still important. So write two more equivalent statements to this one, similar to my even and two example. And then if anyone wants to share one of their alternatives in the chat, I would greatly appreciate it. All right, Monty wrote a nice one. I'm going to write that down here. Switch colors, try blue. Yeah, that's an excellent one. So I am wet if it is raining. The if is still attached to the raining, so they are equivalent. All right. And then the other version, let's see, it is raining if I am wet. That would actually not. So that's a great one. I'm glad you brought that up. So let me put this in a new page. So let's see, I started off with if it is raining, then I am wet. And so this is one of the examples I was hoping we would get to. It is raining if I am wet. So this is not equivalent to the one above, and I'll try to explain why. The if is not connected to raining anymore. And so then we've definitely changed things. So I could rewrite this red one here by saying if it, oh, oops, no, I did that wrong. Okay, it to wet. If I am wet, right? So I'm just going to try and reproduce this red statement in an equivalent way. So if I am wet, then it is raining. So what we've done from the blue to the second red statement is we've definitely changed the order of the premise and the conclusion. And when you change the order like that, this is what's called the converse of a statement. And it does not necessarily have the same meaning as the original statement. And I'll give some other examples of that before. So converse means to switch the premise with the conclusion. So converse, an R of an implication means to switch actually it's called a hypothesis more accurately, hypothesis with the conclusion. And in the original version I gave, it is raining is the hypothesis, and I am wet was the conclusion. Okay. And a converse is not necessarily equivalent to the original implication. So the key when you rewrite it is if you get rid of, if you try to move stuff, if you want it to be equivalent, the if has to stay with the original statement. So if had to go with raining. If I move the if from the raining, then I do change the meaning of the sentence in many contexts. Another way I could reword that blue one is using the word implies instead of if then. So I could say it is raining implies I am wet. Oops. Okay. So there's the idea of a converse. There's a couple other twists we'll do on these implications in a minute, but let's try a new one. So new page. How about this one? If, let's see, if I am at Blue Mountain Community College, then I am in Oregon. So I want you to try two different things here. One, can you write me an equivalent version of this? And I want to two different ways to make an equivalence. And two, can you create for me the converse of this statement? All right, so give it a shot. Write an equivalent version of the statement above, and then write the converse. Converse is where we switch the hypothesis with the conclusion. So the first part after the if, but before the comma, is the hypothesis. Oop, Zoom is in my way. Hypo. Ah. And then this is the conclusion. Write an equivalence and write a converse. I gave two simple examples of equivalence. So those blue ones are the two versions of equivalent statements to the implication. And then the converse I'll do in red. That's where we just switch places, but the if and then stay still. So I would go if I am in Oregon, then I am at BMCC. All right, so that would be the converse. If the original statement is true, sometimes the converse is true and sometimes it isn't. It depends on the implication itself. So a converse is a different statement. It can have a different meaning. If we know that BMCC is in Oregon, and that top implication is true, in this case, this one is false, given that BMCC is only in Oregon, because I could be at Treasure Valley Community College, or I could be just hanging out in Cove, and then I would be in Oregon, but not at BMCC. So that is important. If we go to, let's see, back a couple pages to the even number thing. So if a number is even, then the number is divisible by 2. The converse of that, let's take a look. Can I copy that? Let's try. Got a little more than I wanted, but that's okay. All right, so here's an implication. And so now I'm going to write its converse. So the converse would be if a number is divisible by 2, then the number is even. And it turns out you can play around and say, hey, this converse is true too. So it depends on the implication. So if the original implication is true up here, which it is, it turns out in this case, the converse happens to be true too. In my other case about BMCC in Oregon, the converse was not true when the original implication was true. So a converse is a different statement, it has a different meaning, and it may or may not be true regardless of the original implication. So converse just means switch the hypothesis and the conclusion. Another type of statement that we can make would be an inverse. And an inverse just means negate both parts. Negate the hypothesis and negate the conclusion. So for this statement above, the inverse would be leave everything in the same order, just throw in some negations. So if a number is not even, and remember, be careful about replacing not something with another word, because that gets a little sketchy sometimes. So I'm going to do the safe version there. Then a number is not divisible by 2. So notice the premise and the conclusion stayed in the same order. I just threw in a negation. Okay, so converse means actually pick them up, switch them. So the if is connected to a different statement. And then negation just means throw a not in there. Sometimes it's a little more complicated because we might have to replace none, all with some, or some with none, the rule I gave earlier. All right, so with that in mind, let's do a negation of the BMCC Oregon one. So I'm going to go back a page, and this is more writing than we usually do, so if you need more time to write something down, just say, yo, slow down. So if I'm at BMCC, then I'm in Oregon, so that was the original statement. So we're going to add a third part to this. Can we write the inverse? So give it your best shot, write an inverse for the original statement above. And I'll write down my version. I guess we'll go with red again. So this is my version of the simplest inverse. I leave the hypothesis, but I tweak it to be a negation of itself. I leave the conclusion in the same place, but I tweak it to make a negation of itself. And at BMCC, the easiest negation is not at BMCC. In Oregon, the easiest negation is not in Oregon. And I mentioned earlier, sometimes the inverse is true when the original statement is true, and sometimes it's not. So let's think about this for a minute. If I am not at BMCC, okay, so think of some places that are not BMCC. Well, okay, let's see, I could be in Portland. That is in Oregon. Or I could be in Rhode Island visiting my mom. That's not in Oregon. So since I have one example that shows this is false, it's just false in general. So this sucker right here is false. So my point is, I can rewrite this to be a new statement by just tweaking a negation in both parts. And in this case, even though the original was true, the inverse is false. An inverse means negate a hypothesis and a conclusion. If we take a look at the inverse of the even number example, if a number is not even, then it is not divisible by 2. Okay, so let's see, 3 is not even, it's also not divisible by 2. Pi is not even, it's also not divisible by 2. So I think we can show that any number we pick that's not even, 2 is not going to go into it. So in this case, it's true. Okay. Now, I just gave a couple of examples. 2 examples don't prove something is true, but that's something I could prove with you later in the course. Point. Okay, so there are a couple of ways we can rework an implication so it means the same thing. And I gave a couple of simple ways to do that. By leaving if by the premise, even if we state the conclusion first. Okay, so that's a possible way. The other way is to put the word implies in between and just ditch if and then. So those are linguistically the same statement. So converse, inverse, another tweak we could make is called a contrapositive. Isn't that a cool word? Contrapositive. And a contrapositive means to do both, take the converse and the inverse. So see if you can write down what you think the converse and inverse together at the same time of the original statement would be. It's going to be different from the red one, different from the blue one. It's going to be a whole new statement. What do you think it should be? Write down your version of that. And we're also going to try that for the BMCC Oregon, if you whip through that quick. I'll write down my version. Okay, so I think it should be if a number is not divisible by 2, then the number is not even. So I had to take the original conclusion, state that up front, negate it. So it's got to have an if, the old conclusion negated, and then I take the premise, throw it as the conclusion, and I negate it also. So if a number is not divisible by 2, all right, so pi, then it is not even. Yep. If a number is not divisible by 2, 3, then it is not even. Okay, so a couple of examples. I'm going to make the broad generalization that this is still true. So notice here we have a true, 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 true. They're all true. Jump back to the example about BMCC. Let's write the contrapositive of that. Oh, pen freak out. All right, I think it would be this. If I am not in Oregon, so I negate the conclusion, state it first with the if, then I am not at BMCC, negated hypothesis at the end. So we switch and negate. That's called a contrapositive. So let me see. I am not in Oregon. Let's take that as fact. Okay. Could be anywhere. Could be Portland. BMCC is not in Portland, so I'm not at BMCC. Okay. I'm not in Oregon. I'm in Egypt. BMCC is not in Egypt. I'm not at BMCC. So I think I'm starting to lean toward that this last statement here is also true. All right. So point. there are three main ways to rewrite an implication that have a different meaning that may or may not be true. And the main ways are the idea of a converse, which is to switch, an inverse, which is to negate, and a contrapositive, which is to switch and negate. If the original statement is true, the converse or inverse may or may not be true. The contrapositive, it turns out, will always also be true. If the original statement was false, the contrapositive would also be false. It turns out the contrapositive and the original are linked in fate. So is
that in all cases?
Yeah, this is the crazy thing, right? So I've got some simple ways to write equivalences, but it turns out the contrapositive is another equivalence. And the important thing about this for mathematics is sometimes somebody will come up with this statement that they think might be true, but they're having a hard time proving it. And if they rewrite it as the contrapositive, it's sometimes easier to prove true. Sometimes they're both hard and it doesn't matter, but it just gives us an equivalent way to talk about the same idea. So I'm just going to draw a Venn diagram. Actually, no, we've been at this for over an hour. We're going to take a 4-minute break, move around a little bit because we've been kind of sedentary for a little bit. And then I'll draw some pictures of Venn diagrams about how this stuff works too. And we'll take a look at a few homework problems. So take 5, stand up, move around, shake a leg, get a drink of water, run up a pyramid or down, stretch, do a little yoga. Let's see, what time does my thing say? 4:14. So at let's say 4:18, we'll get busy again. Stop the recording.